In this video, we are continuing our Chapter 1 review, and we're going to do some practice problems that involve linear transformations. Okay, so I first just want to review a couple of key definitions. So remember that a function t that has domain Rn, which means I'm plugging in vectors that have n entries, and codomain Rm, which means the vectors I get out of the function have m entries. Well, that function is called a linear transformation if it satisfies two key properties, these two key properties here. As long as it satisfies those two properties, that function is called a linear transformation. Okay. All right, so I first want to review two key terms. What does one-to-one mean? And what does the word onto mean? And I'll try to draw pictures of these to kind of review what they mean visually. So we say that a function t is one-to-one. Another word for one-to-one is it's something called injective. It's one-to-one if when you have two, the way I read this is if I have two outputs, one of the outputs is t of u and one of the outputs is t of v. So if I have two output vectors that are equal, the only way for that to happen is if their inputs u and v were the same. So the only way for two outputs to be the same is if the two inputs vectors u and v are the same. Well, that's equivalent to saying that whenever my input vectors are different, whenever u and v are different, then t of u, their output vectors t of u and t of v, well, those output vectors are not going to be equal to. So I'll put a slash through that equal sign. So those are just two ways of saying the same thing, of what it means for a function to be one-to-one. Well, on the flip side, then what would it mean for a function to not be one-to-one? A function is not one-to-one if I can find two inputs that are different where their outputs, t of u and t of v, are in fact equal to one another. Okay, so let's just review, well, what do the pictures of these scenarios look like? What does it look like if something is one-to-one versus if something is not one-to-one? Okay, I think it's easier to draw something that's not one-to-one, just a little bit quicker. So I'm going to let this circle represent my domain. So my domain here, I'm calling it Rn, my domain. Those are the vectors I'm plugging in. And the codomain, the vectors I potentially could get out, are in Rm. So something is not one-to-one if we can find two input vectors in the domain. Let's call it u and v, whose output, so I'm going to draw an arrow connecting them to their output, whose output vector is the same. So t of u, if that is equal to t of v, okay, that would make this thing not one-to-one. So if I can find two different inputs that have the same output, that would not be one-to-one. So let me box that. That is a picture of what a not one-to-one thing looks like. Multiple inputs corresponding to the same output. So then what is the picture of a one-to-one function? So something that's one-to-one is if I draw my domain Rn, and if I draw my codomain Rm, something that is one-to-one would have the property that if I look at all the input vectors, I mean, there's going to be infinitely many, but if I look at all the input vectors, they need to have different output vectors. So whatever the output of this one is, well, that's got to be different from the output for this next vector. And that's got to be different for the output of this next vector. And, that's got to be different from the output of this next vector. And also, maybe there's some vectors in the codomain that didn't have anything in the domain that kind of gets it as an output. Okay, that could happen. So this is the picture of a one-to-one function. All the inputs have a different output vector. All inputs have different outputs. Okay, that's just a quick review of one-to-one versus not one-to-one. What about this other term, onto? We say that a function t is onto, another word for onto is surjective. Onto means if I look at the equation tx equals b, that's going to have a solution. The solution is the vector x for any vector b in the codomain. Okay, so that's the same thing as saying that no matter what vector that I pick in the codomain, no matter what vector that I pick over here in this codomain circle, well, there's always going to be something in the domain that reaches it. There's always going to be some input that lets us reach that output, no matter what output vector we picked. Okay, so the picture for an onTo function is, well, whatever my domain is, let me just call it domain, and whatever my codomain is, well, if I draw all the vectors in the codomain, I'm just going to draw 3 dots. Just going to draw 3 dots. Well, there's going to be things in the domain that get mapped to all of them. So there's some vector that maps to this first output. There's some vector that gets mapped to that second output. And in fact, there might be multiple vectors that get mapped to that second output. That could definitely happen. And there's got to be something that maps to this final output. So there's got to be things that map to everything, every vector in the codomain. That's something that is onTo. Everything in that codomain gets reached as an output. A function is not onTo if that doesn't happen. So just to give myself room, let me move this picture a little bit. I actually want to move it here. I need some room to write. Function is not onTo if there is some vector b that is in the codomain Rm such that the equation Tx equals b has no solution. That would be saying, well, there's some vector in the codomain that we actually don't get as an output. So a not onTo picture, something that would not be onTo if I draw a circle for the domain. And the circle for the codomain is if I have a couple of codomain vectors. Maybe there's some codomain vector that never gets reached. So maybe there's something that reaches the first one, there's something that reaches the second one, maybe there's nothing. Maybe there's multiple things that reach some of these. But there's something in the codomain, at least one thing in the codomain, that never gets reached as an output. That would not be onTo. Okay. So I think having those pictures in mind is helpful in getting a better visual understanding of what these terms mean. Let's look at a practice problem. So this problem says, suppose T with domain R3, so that means I'm inputting vectors with 3 entries, and codomain R2, so the output vectors of 2 entries, is linear. Which of the following statements would imply that T is onTo? Briefly explain, and there may be more than one right answer. So there are these 3 parts. In some of these, they may be implying that T is onTo. And there may even be multiple statements here that mean T is onTo, and we have to identify them. Okay, so let's look at these. Part A says, the equation Tx equals b has infinitely many solutions for every vector b in R2. So you know what? I actually want to give you an opportunity to try it first. So pause the video for about 4 minutes. I want to give you time, hopefully, to try multiple parts of this. 4, 3, 2, 1, pause it, and try it for about 4 minutes. All right, so hopefully did that. Hopefully paused it and tried it for about 4 minutes. Let's talk about it together now. Okay, so part A is saying Tx equals b has infinitely many solutions for every b in R2. Well, something is onTo if the equation Tx equals b will have a solution for every vector b in the codomain. And this is saying that. Actually, it's telling us a little bit more. It's telling us not only is there a solution, there's actually infinitely many solutions. Okay, so in part A, it is onTo. It is onTo since Tx equals b has a solution. It does indeed have a solution for every vector b in the codomain. And the codomain here is R2. Okay, in fact, the problem told me a little bit more than I even needed. It told me not only is there a solution, there's infinitely many of them. But that's still onTo. Okay, all right, let's look at part B. Part B is saying that if I look at the equation Tx equals the vector 4, 2, that is consistent. Okay, so that means consistent means there is a solution. In other words, I am able to get the vector 4, 2 as an output. There's some vector I could plug in that will get me to that output. So would that definitely mean that t is on 2? Well, not necessarily. Not necessarily on 2, because this is only telling me information about one output. Only telling me information about one output. You know, we know 4, 2 is an output, but we would need to know that every vector b in R2 is an output, but we don't know. We don't know if every vector b, sorry, I should say every vector b that's in R2, every vector b that's in R2 is an output. Okay, so because of that, part B does not necessarily mean that t is on 2. Okay, and then finally we have a part C here. So part C. The solution set to the equation tx equals 0 is a line through the origin. The solution set to that equation is a line through the origin. So we're looking at the equation t of x equals 0, 0. Okay, so the output vector here is in R2. And the input vector, well, the problem tells me my domain is R3. So the input vector is something that's in R3. Okay, so the input vector is something that's in R3. Okay, so the problem's telling me that not only is there a solution to this, but it happens to be a line through the origin. So let's write an equation that says something like that. So x, the solution, the general solution, what would it look like if it's talking about a line through the origin? It would be, you know, it would be like a vector that's got 3 entries, because my domain is something in R3. So there's going to be 3 entries. Maybe I'll just call them A, B, C. You know what? Let me just put stars for each of those spots. There's a first entry, there's a second entry, there's a third entry, some vector. And then there's going to be a free variable in front of it. I don't know, some free variable. Maybe I'll call it x2 for the time being, but some free variable. Doesn't necessarily have to be x2. It could have been x3 or x1. But there's some free variable. Okay. Because that's what a line looks like. It's all of the multiples of one vector. So this would be a line. So the key thing that this tells me is how many free variables I have. This tells me I have 1 free variable. Okay, so at this point, one more time, what I want you to do is pause the video and see if you can now answer the question. Because originally I think part C was the toughest out of them. So pause the video for a quick minute, see if you can answer the question now. 4, 3, 2, 1. Pause the video for a minute, see if you can continue it from here. All right, so hopefully you did that. Now let's check in, let's talk about it together. Okay, so I got 1 free variable. It would be helpful to know how big the corresponding matrix is for this transformation. Okay, so when I think about this equation, I could rewrite this as like A times the vector x equals the vector 0, 0. Okay, let's think about the sizes of everything. So the vector that I'm getting out, that's a 2 by 1 vector, 2 entries, 1 column. The vector x I'm plugging, that's 3 by 1. It's got 3 rows. So for that to work out, A would have to be, well, it's got to have the same number of columns as x has rows. And then A would have to have 2 rows. A would have to have 2 rows that it ends up working out to a 2 by 1. Kind of one of the tricks that you can do is, well, the 2 middle numbers here kind of cross out. And when you do that, you're left with a 2 by 1. And now they match up on both sides. Okay, so A is going to be a 2 by 3 matrix. And I know it has 1 free variable. 2 by 3 matrix. And there's 1 free variable. Okay, so that means 3 columns. Well, one of them corresponds to a free variable, which means, well, there's 2 pivots. That means there's 2 pivots since A has 3 columns. But if there's 2 pivots and A has 2 rows, well, that means each row has a pivot. Each row has a pivot. And one of our key results from our section about onto and about one-to-one is if each row has a pivot, well, then the transformation is onto. It is onto. All right, awesome. So part C implies that this transformation is onto. Part A also implies it's onto, but part B doesn't. Okay, so it's a very good conceptual problem here, really testing our understanding of onto, and part C especially connecting it with other ideas of like free variables and pivots. So a lot of rich stuff in that problem. Okay, so I want to wrap this video with one final example where we find the standard matrix for a transformation. That was one of the other big ideas in our section on linear transformations. So this transformation has a domain R2, plugging in vectors with 2 entries. The codomain is R2, so I'm outputting vectors with 2 entries. And it reflects points across y equals x, and then it scales their y component. That means multiplies their y component by 1/2. Okay, so find the standard matrix, and then it says use it to figure out if the transformation is 1-to-1 or onto or both or neither. Okay, so recall the formula for the standard matrix. I'm going to call the standard matrix A. And the first column of the standard matrix is T of E1. Remember, E1 is the first column of the identity matrix. So because my domain is R2, I'm talking about the 2x2 identity matrix. I'll call that I subscript 2. So it's a 2x2 matrix with 1s along the main diagonal, and everywhere else there's got to be 0s. So E1 is the first column of that identity matrix. That is E1. Okay, and then, well, the next column is T of E2, where E2 is the next column of the identity matrix. And now I've done all the columns of this identity matrix, so that's when I stop. Okay, if my domain had been bigger, like if it was R4, then my identity matrix would have been a 4x4 matrix. And then I would have gone with the columns up until T of E4. I would have had 4 columns then. Okay. All right, so I got to figure out what these things are. So to do that, let's draw a picture. So I'm going to draw some axes. And let's draw these vectors, E1 and E2. So E1 is 1 unit along the x-axis. Let me switch to a different color. 1 unit along the x-axis. So E1 is the vector 1, 0. E2 is 1 unit up along the y-axis. That is E2. That is 0, 1. And now what's going to happen to these vectors is first, they get reflected across the line y equals x. So let's draw y equals x. Okay, so with the vector E1, what's going to happen to the vector E1 is it's first going to get reflected. So this tip of it's going to get reflected to the other side of that diagonal line. So I reflect it perpendicularly across that diagonal line. Okay, so it's going to end up here. It's going to end up being exactly the same as E2 actually. And then it says to scale the y component by 1/2. Multiply the y component by 1/2. So the y component of this vector is now 1. If I multiply that by 1/2, it becomes half as long. So that is my end result. T of E1 ends up becoming 0, 1/2. So that is going to be the first column of the standard matrix. It is 0, 1/2. So I'm going to highlight that. T of E1, I just figured it out. It's 0, 1/2. Ooh, not loving that color, but I got it here. 0, 1/2. Okay. All right, now let's do the same thing to E2. So with E2, when I reflect E2, it gets, if I flip it perpendicularly across the line y equals x, well, that'll end up the same spot as E1. Let me put that in a different color. You know what? Let me just make a new picture. Let's say this first picture was just for E1. Let me make a separate picture for E2 just because it's getting a little cluttered now. So E2 is the vector 0, 1. Let's draw that diagonal line, y equals x. If I reflect it to the other side of y equals x, I end up with a vector 1, 0. Okay, and then I got to scale the y component. So this vector is 1, 0. I got to scale the y component and multiply it by a half. So multiply this y value by 1/2, but 0 times a half is just 0. That doesn't change it. Okay, so it stays there. So for this one, t of E2, what I get when I transform E2, well, it just ends up being 1, 0. Okay, so now I know the second column. Let me highlight this in a different color. The second column, t of E2, that happens to be the vector 1, 0. That happens to be the vector 1, 0. Okay, nice. And that is my standard matrix. Okay, so that matrix will describe this transformation for us. Okay, so then it says use the standard matrix to determine if the transformation is on 1, or on 2, or both, or neither. So to do that, I need to row reduce it. So this was this part A? No, there was no part A and B. It was just multiple parts in the same problem. So I got to row reduce it and put it in echelon form. So I'd have to swap my rows to do that. So I'll get 1/2 0 on top, and then 0, 1 on the bottom. So I am swapping row 1 with row 2. Oh, now I can see the pivots. I see there's a pivot here and a pivot here. Okay, so we have a pivot in each row. And when I have a pivot in each row, it means my transformation is onto. Also, I have a pivot in each column, coincidentally here. I have a pivot in each column as well. And when that happens, that means the transformation is 1 to 1. So this is both onto and 1 to 1. That's my answer.